It's important to be able to do multiple kinds of conversions. And so this brings us to the teaching model number 3. In the teaching model number 3, we're starting to look at the two-step conversions. We've looked at conversions that involve Avogadro's number, that's going back and forth between the number of atoms and the amount of substance in moles. And we've also looked at conversions that involve the amount of substance and the mass. And of course, to do that, you need the molar mass. Now in this chart, I've got that word atoms. It will become more apparent in chem activity 6 why we've included that number, because this chart is going to expand. And you'll see that we'll be working at the level of atoms. We'll also be working at the level of molecules. So right now, it's number of atoms, the amount of substance of those atoms in moles, and then finally the mass in grams of that particular element whose tiniest particles are atoms. Okay, so I do want to emphasize once again that it is possible to do these sorts of conversions, and we've seen that we can go from atoms to the amount of substance, and we can go from the amount of substance to the mass. And likewise, we should be able to go from the mass to the amount of substance and finally to the atoms. In terms of this approach, it's not really possible to go from atoms directly to mass. And I'm going to keep on encouraging you to always be using the amount of substance as that middle ground that allows you to interconvert between those two kinds of quantities. So let's look at the key question number 3, which will be an example of using this chart. Now on the screen you won't see the chart anymore, but of course you'll have it in your booklet, so you'll be able to refer to it. So let's take a look. So this is the key question number 3. Use a two-step approach to calculate the mass in grams of 3.011 times 10 to the 23 atoms of solid aluminum. Note, I actually tell you to use a two-step approach in a normal assignment or test. I won't tell you that it's a two-step or a three-step. You will need to know that. But right now, because we're learning through this, I'm just emphasizing. Once again, identify what the quantity is. Okay, so the quantity we're starting with is the 3.011 times 10 to the 23 atoms of solid aluminum. We want to go from atoms, and ultimately we want to convert to the mass in grams. But to be able to do that, we have to first of all convert the number of atoms to the amount of substance, the amount of aluminum in moles. The conversion factors to do this: Avogadro's number in the first case. Note that in the numerator it's 1 mole of aluminum atoms divided by Avogadro's number. And then once we have the amount, we can convert to the mass in grams using the molar mass of aluminum. Once you've done this work, as I say, either in your head or explicitly writing it down, the calculation is very straightforward. And so the calculation would look something like this. We first of all write down our quantity, including its units. So therefore it's 3.011 times 10 to the 23 atoms. We multiply by the first conversion factor, which will allow for the atoms to cancel. And at that point we'll have calculated the amount in units of moles. Then we multiply by the second conversion factor, which is the molar mass conversion factor, till finally we end up with the answer of mass of aluminum. And so just to point out, in terms of the units canceling, so we'll have atoms cancel here, we'll have amount in moles cancel, and we end up with the quantity in mass of aluminum solid. Now it is important to kind of step back and make sure that this answer makes sense, in that we started with roughly half of Avogadro's number, and we end up with a mass of aluminum solid that's half the molar mass. And so indeed, this answer makes sense. So in a sense, this is a two-step conversion. You don't need to, first of all, calculate the amount and write that down, and then from the amount calculate the mass. You can do it all in a continuous, beautiful stream of mathematical equations. So you're less likely to make mistakes when you use this approach. So what follows are 3 more exercises. I think you know the strategy. I'm going to ask you to stop the video and give them a try, and then we'll go through them. Now, in these exercises, you'll see that gradually I'm reducing the amount of, in a sense, scaffolding, and that we're going to make writing the unit plan as well as explicitly writing out the conversion factors less explicit. That is, you're not going to be writing them out, not unless you wish to, not unless you feel that they're going to be helpful in solving the problem. Or another way is maybe you can write a short form, and I'll show you that when we get to there. So let's take a look at these exercises. You get exercise 4, and then I'm going to ask you to look at 5 and 6. So stop the video, give these a try. Okay, so let's take a look at exercise 4. Now this one I've still included the scaffolding. The step, of course, to begin with is to identify what the quantity. The quantity in this case is the 16.90 grams of gaseous neon. So we're starting with a mass. We ultimately want to convert to the number of atoms. We've got to go through the amount, first of all, the amount of neon, then to the number of atoms. We use these conversion factors. The first one involves the molar mass of neon, going from the mass to the amount. Just grab that mass from the periodic table. The next one, of course, is the Avogadro's number. Plugging all of these into an equation, something like this. I'm starting with 16.90 grams. It's helpful to realize that that 16.90 grams is a little less than the molar mass of neon. And so you can see that the actual number of neon atoms is a little less than Avogadro's number. So this answer does make sense. And so we're addressing the question, explain why your answer makes sense. In terms of canceling units, I see that moles of neon atoms cancel, moles of neon atoms cancel, and mass cancels and mass cancels. For the next problem, I'm also starting with 16.90 grams, but this time it's of carbon. Now we have a slightly different result here. But let's not get ahead of ourselves. First of all, the quantity is 16.90 grams. So we've got mass. We're going to ultimately calculate the number of atoms, convert to the amount, and convert to the number of atoms. Now you can see this time I didn't bother writing out the conversion factors, but even just writing out this unit plan organizes me. I got to go from mass to the amount to the number of atoms. And then in doing the calculation, I will insert the appropriate conversion factors. So 16.90 grams, then we've got the conversion factor involving the molar mass of carbon, and then the conversion factor involving Avogadro's number, and then finally the number of carbon atoms. Again, I ask, explain why your answer makes sense. Well, note this time the mass of carbon that we have is greater than its molar mass. And therefore, the final answer is a number of carbon atoms that's greater than Avogadro's number. And then lastly, now this problem is a little bit different. And I think you may want to make a unit plan, but the unit plan might be somewhat atypical, but it will help organize you. What mass of element iodine contains the same number of atoms as 25 grams of element chlorine? So in a sense, we're starting with a mass of chlorine, so that's the quantity, and same number of atoms. Well, that means, of course, the same amount. So if we can find out the amount of chlorine, and then it's going to be the same amount of iodine, and that same amount of iodine can then be converted to mass. So putting this down in terms of a unit plan, it could look like this. Mass in grams of chlorine, which I can convert to the amount of chlorine, which I can convert to the amount of iodine. It's going to be the same amount, so it'll be a 1-to-1 ratio. Once I know the amount of iodine, I can convert that to the mass of iodine. Now note, I have used the correct formulas for elemental chlorine and elemental iodine in that they exist as diatomic molecules. I know that you will get the same answer had you used atomic chlorine and atomic iodine. Right? But technically you should be using these diatomic molecule formulas and masses. So therefore the calculation would go something like this. The 25 grams of chlorine convert to the amount of chlorine, so the mass will cancel. We end up with the amount. Now I could convert to the actual number of molecules of chlorine using Avogadro's number, but then I would have to convert it back to the amount of iodine. using Avogadro's numbers. So that effect will just cancel. So I'm going to leave it at the amount, that is the number of moles. Note that this middle conversion factor is saying that we want the same number. So 1 mole of iodine molecules, 1 mole of chlorine molecules. And so those will cancel. That cancels there, and that cancels. And so finally I'll end up with the mass of iodine solid. It's hard to, in a sense, check your answer other than, if you think about it, because the molar mass of iodine is greater than the molar mass of chlorine, I would expect that the final mass that I'll end up with is a mass that's going to be bigger. And if you compare the molar masses, you can see that iodine's molar mass is more than 3 times bigger, and the final mass that I end up with here is in fact 3 times bigger. This ends what I'm going to discuss in terms of the video in Chem activity number 5. We will be looking at a number of activities in class.